Thank you. Thank you very much. And once more, thanks to the organizers for giving me the chance to present this recent work here. Yeah, I'm also glad that this is my last talk at this conference. So, okay. So it has two parts. The first part is essentially motivation, maximal subgroups or finite classical groups. I will tell you about the ASCHBACHER approach to maximal subgroups and what I mean by C2 obstructions. And then, which leads to the main objective of this work I'm going to present, and this is imprimitive representations of finite quasi-simple groups. I'm going to tell you what I mean by this, what is known in characteristic 0, in positive characteristic. I will present you the reduction theorems, and then finally in the last two slides, some more technicalities about how to express the results in terms of LUSZTIG series of characters. Okay, let me just start with this is a joint project which lasts for a very long time. It started in 1999 with Bill Hewson and Kai Magath. And it's the project to classify, in a sense, pairs, a finite quasi-simple group G, a finite dimensional vector space over, for this slide, an algebraically closed field little k, and an absolutely irreducible and imprimitive representation G into SLV. Okay, since G is, what is a quasi-simple group? A quasi-simple group is a perfect group. So every representation of the perfect group into GLV will end up in SLV. So this is no loss. And it's perfect. And modulo the center, it's simple. So in particular, it's a non-abelian simple group modulo its center. Otherwise, it couldn't be perfect. Absolutely irreducible is a representation if the image of the corresponding representation of the group algebra KG is all of the endomorphism ring of V. Then it's absolutely irreducible. And imprimitive, it is imprimitive if the vector space can be decomposed into a direct sum of subspaces, at least two, which are permuted by the action of G. So these in particular, all these subspaces have the same dimension. Equivalently, one can say V as a KG module is induced from a KH module V1. And H is the stabilizer of one of these subspaces. So induced representations, induced from proper subgroups. These are the imprimitive irreducible representations. Okay. Finite classical groups. What are the finite classical groups? Okay, K is now, from now on, little k is a finite field, an n-dimensional k vector space, and X a finite classical group on V. To be specific, I just enumerate these groups. SLN Q, where n is at least 2. Q can be any prime power. SPN, where n is even. Omega n, well, omega n is just, you may think of omega n of Q just as the commutator subgroup of SON. The commutator subgroup. And there's one in odd dimension, and there are two in even dimension. So these are the classical groups I'm going to consider. Or V is a vector space of dimension n over FQ squared, and X is the unitary group. So this is our notation for the unitary group. Some people might want to write SUN of Q squared to emphasize the underlying general linear group. But anyway, so in cases 2 to 5, in cases 2 to 5, the group X is the stabilizer of a form, of a non-degenerate form, which may be symplectic or a quadratic form or a Hermitian form. So these are the form stabilizers, of non-degenerate forms, respectively SLNQ. Okay, so what is the ASCHBACHER classification? The main objective is to determine the maximal subgroups of X, of these finite classical groups. I mean, that's very natural. There's this ASCHBACHER approach. It's ASCHBACHER's subgroup classification theorem. I don't want to tell you too much about it, but ASCHBACHER has a way of defining 9 classes of subgroups. The first 8 classes are, in some sense, associated to the geometry of V. For example, C1, those are the groups which are maximal with respect to acting reducibly on V. Yeah, so if you like, parabolic subgroups. So I switch to column notation, okay, in this talk. So these are the C1 subgroups. And ASCHBACHER says, well, if H is a maximal subgroup, then it belongs to one of these classes. Well, and but conversely, an element which belongs to one of these classes need not be maximal. So one has to find out when is a maximal element in one of these classes a maximal subgroup. Oh, well. A lot of work has been done towards this direction by Kleidman and Liebeck and Brayholt and Roney-Dougal, Kolba-Roney-Dougal. They determine the maximal subgroups in X of the members of all classes except for S of X. This A mod means among many other things. Okay? So these are 2 books I'm referring to. So in a sense, the maximal subgroups of X are known unless a group H belongs to the class S of X. So what is the class S of X? Again, I just have my situation. X is a classical group inside SLV, and H is a proper subgroup. Then, well, H is in this class S of X. S stands for simple. If it's the normalizer of a group G, which is quasi-simple, and also G acts, the embedding of G into X and then into SLV is an absolutely irreducible representation. So the group G itself acts absolutely irreducibly on V, and it's not realizable over a smaller field. This representation phi, which just means that you don't have such a factorization with a representation G into some SLV node where V node is a vector space over a proper subfield of K. Or, I mean, to put it more easily, there is no basis of V such that all the matrices of G with respect to this basis can be written over a subfield, over a proper subfield. So this is the class S of X. And how do the elements of S of X look like? I think it's quite important to have a picture. So let's look at such a group S of X. Then, well, you have the center of X. Z is the center of X. Okay, and then you have your group G. So, and this is Z intersect G, which is the center of G. So the group is quasi-simple. It may have a non-trivial center. But the centralizer in X of G is the same as the centralizer in X of H, is the same as the center of G, is the same as the center of H, since this representation is absolutely irreducible. All matrices which commute with the matrices of G are just scalar matrices. And the scalar matrices in X are exactly the center of X. So this is the scalar matrices. And well, you have Z times G, you have H, and you have X. Okay, so this is the subgroup H. This is a subgroup of the auto-automorphism group of G just by the very construction, and therefore it is solvable. And therefore, since this is abelian, this is solvable, and G is quasi-simple, the fitting subgroup, the generalized fitting subgroup of H, or the is Z times G, and G is just the how would you say that, the end term in the commutator series. The end term in the commutator series, H infinity. This group what is it? H modulo Z. So this group is almost simple. You see here, you have a simple group. So G modulo Z is simple. So this is almost simple, which means that it fits into the series, short exact sequence. So this is a simple group. And this is this simple group, which I called S here. So S. Yeah? Okay. So this is the structure of the groups H we are going to consider. And we want to know, is this a maximal subgroup? Is this a maximal subgroup? So which embeddings of quasi-simple groups into classical groups give maximal subgroups in this way? This is the problem that is left. Well, if not, then there is a larger group, K, obviously. And then I don't repeat the definition of the ASCHBACHER classes, but these are set up in such a way that only, so this K must belong again to one of these ASCHBACHER classes if it's maximal. So let's assume that K is maximal. And then it must be C2 or in C4 or in C7 or again in S of X. So there could be a larger group which is again in S of X. I will show you examples. So in this talk, so this has C4 and C7 I will not address here. And S of X, this is the topic of many investigations of my colleagues. So essentially it means you have one simple group sitting inside a larger one, and you have representations of the larger group. When is the restriction irreducible? I mean, this is what it amounts to. Because if K is again in S of X, the embedding into SLV is absolutely irreducible. This was also already absolutely irreducible, so it must restrict irreducibly. But this is a difficult thing. Well, if this K is in C2 of X, we say that this is a C2 obstruction. So what are the C2 subgroups? So these are the groups that act imprimitively in a sense, but compatible with a form structure defining X. So you have so we say H is in C2 prime of X, and the prime is just meant to denote the subgroups of X which are subgroups in groups of type C2 of X. You see, the C2 of X in the sense they have some maximality condition attached to them, and I want to look at all subgroups of those. So these are the subgroups such that H, so H is in C2 of X prime if H permutes vector space decomposition with at least two direct summens, and if X is defined by a non-degenerate form, the VI are either non-degenerate and pairwise orthogonal, or T is equal to 2 and the two are totally singular. So these are the options. In particular, if H is in C2 prime of X, the embedding of H into X is an imprimitive representation. And the elements of C2 of X are the full stabilizers of such decompositions. Just the full stabilizers. Okay? Okay, so what is the C2 obstruction? I think I'm going to prove something here. Again, I have this situation. G is H infinity, is the largest, the smallest term in the commutator series of H. And then there exists a larger subgroup K, which is in C2 of X, if and only if H itself lies in C2 prime of X. So there is a C2 obstruction to the maximality of H, if and only if H stabilizes decomposition as here. Well, only if direction is trivial, because every subgroup of a C2 of X group is a C2 of X prime group. Okay, so suppose that H stabilizes the decomposition, and suppose also let K denote the full stabilizer of this decomposition. So you have one decomposition, K is the full stabilizer, and I assume that K is larger than H. But the full stabilizer, you see, what are full stabilizers of decompositions? I mean, if you look at SLN, so it consists of this Levy subgroup, which is corresponding to the blocks, and all block permutations of these, okay? And essentially, except for a degenerate situation, the last term in the last term in this H infinity is something here, which does not act absolutely irreducibly. Just from looking at the cases, looking at the description of all the subgroups in C2 prime of X, we see that K cannot act absolutely imprimitively, or at least K infinity cannot act absolutely. The last term in the commutator series. Yeah, the last term in the commutator series. Yeah. The commutator series, I mean, you look at the commutator and the commutator and the commutator, and then it stabilizes at G. It stabilizes at G because G is perfect. Cannot have any, so G prime is G, and then it stops. Yeah, so just by looking at the description in the individual cases and fiddling around with some small cases, one sees that if you have a C2 of X group, then it cannot act. Its last term in the series cannot act absolutely irreducibly. And again, if H is in C2 prime of X, then G is in C2 prime of X prime, and then this embedding is imprimitive. Let's look at an example. MATHIEU group M11 once more. I have used it many times as example, yeah, but it's a nice example. So let's look at such an embedding of M11 into a classical group. And it's because M11 is so small, all these embeddings are known up to equivalence. All these embeddings are known. I mean, it is known what are the degrees, what are the classical types of the group X, and so on and so forth. Then I identified G with a subgroup of X, and since G does not have any sure multiplier, the sure multiplier is trivial, the normalizer in X of G will just consist of the center of X times G. Center of X may be non-trivial, of course. And it will be in general. And so the question is, will this give a maximal subgroup? And the answer is no, except for one particular case. There is a 5-dimensional representation of M11, which is realizable over the field with 3 elements, hence over no smaller field. And it goes into SL25 and into no other classical subgroup of SL53. And this gives a maximal subgroup. So in this case, the center is trivial. But for example, you have an S abstraction for a 10-dimensional representation, which ends up in omega 10 plus, because there is an A11 in the way. So M11, of course, embeds into A11, and A11 has the same 10-dimensional representation. Or M11 embeds into a 55-dimensional prime field, FL, if L is at least 5. I mean, you have constructed this in one of the practical sessions. But then this is an imprimitive representation. It's induced from a subgroup, and therefore this is not. This does not give a maximal subgroup, but there are many other groups in the way in this particular representation, So all these groups have this 55-dimensional representation, and they are embedded into SO55 in such a chain. There is a 10-dimensional representation, which does not go into any proper classical subgroup of SL10-3, but there are 2M12 is in the way. And finally, there's a 24-dimensional representation of orthogonal type, which sends you into omega 24 minus of 3. And there is this SL53 in the way. So this, again, has this 24-dimensional representation. And they are, you can do this for all other representations. So Kaimagard and I have checked this. But is this example typical or not? This is very atypical, I would say, because M11 is so small. In general, you will get a maximal subgroup. Yeah, just for you as an exercise, if you want to really learn about this, try to find out whether the embedding of the monster over the field with two elements, which lands into this omega minus of 196882, does it give a maximal subgroup? You see, the monster you think is a large group, but this is really large. So the monster is very tiny inside this group. Very, very tiny. Is it maximal? Well, at this stage I haven't checked, but I would say yes. But this has to be checked. So this leads to the main objectives. Determine the triples, allowing a C2 obstruction. So this is our project. Determine all triples GKV such that G is a finite quasi-simple group, K is an algebraic closed field, V is an irreducible imprimitive KG module, then we don't have to worry about absolutely irreducibility if we start with algebraically closed fields. And then, of course, we need a faithful representation of G in general, because otherwise we could just work with a smaller group. Well, I have been talking about the applications on the maximal subgroup project for finite classical groups, but this project doesn't really restrict to fields of characteristic P, so I include the case of characteristic 0 here. And this really is a model for the desired classification in all cases, and it has provided most ideas. So what are the finite quasi-simple groups? So why can we do this? Yeah, because we have a list of the finite quasi-simple groups, because we have the classification. So we just look at each quasi-simple groups in turn. So it's a covering group of a sporadic simple group, it's a covering group of an alternating group, AN, or it's an exceptional covering group of a simple finite reductive group, for example, the 2E6 of 2, twisted E6 of 2, as an exceptional covering group. With a center of order 2, or 6, if you like, the universal covering group. Or it's the TIT simple group. Or it's a quotient of a quasi-simple finite reductive group. So I have excluded these because not all of these groups are, in a sense, what we call finite reductive groups. But I will tell you what the finite reductive groups are. What are the finite reductive groups? So this is the modern approach to these quasi-simple groups of Lie type. You start with a reductive algebraic group over a field algebraic closure of Fp. You take a Steinberg morphism. Well, for you, it's just the best to think of GLNF. And F would be a Steinberg morphism, an example of a Steinberg morphism if it sends every matrix entry where Q is a power of P and P is the characteristic of F. Okay, so these are the Steinberg morphisms and generalizations of them. Essentially, this is the only examples, and you might have Steinberg morphisms such that some power of the morphism is like this. Yeah? And then the set of fixed points is a finite reductive group, as you can see. If you take the fixed points under F, you get GLN FQ. And in a sense, this gives you a nice description of all the finite GLN FQs or FP to the power of, FP power, inside here. For what comes, I also need the notion of a Levy subgroup. So a Levy subgroup is split if it's a Levy subgroup, if it's an F-stable Levy subgroup, and it lies inside some F-stable parabolic. So here the Levy subgroups would be just block diagonal matrices. Yeah, because all these lie in F-stable parabolic, you see. And such pairs, so if you go down to the finite group, then you get what is called the Levy, parabolic subgroups in the sense of groups with Bn pair and their Levy complements. Okay. So what is known? So all these triples which we want to classify, I've just written them once more here on the slide, are known now. I hope so, yeah. It's one of the most difficult things I ever did in my life. And even this morning, before I came here, I've been working on this paper with Kai Magath and to settle down some, to formulate the last half sentences of the proofs, you see. Well, here are some references for the sporadic groups. So last year, a memoirs of the American Mathematical Society appeared where we have done many cases, in particular the sporadic groups. The alternating groups, this is known for a long time by a work of Djokovic and Malzahn from '76. Nett and Nöske, so these are people from RWTH Aachen, they have done the double covers of the alternating groups. And then the exceptional, so the groups with an exceptional covering groups and the TIT simple group were also done by Bill, Kai, and myself. And this is the paper I'm referring to, the finite reductive group. So there will be a new paper being made public soon, where we do the quasi-simple groups. So here we did finite reductive groups arising from algebraic groups with connected center, because there the linear LUSZTIG theory is much less difficult. In defining characteristic, it goes back to a result of sites. So what are the imprimitive representations of quasi-simple finite reductive groups over fields of the same characteristic? There are only a few. So these are the groups, and V is the Steinberg module. Well, in this case, not always representing the group faithfully, like in. But anyway, so this was done by Gary Seitz back in '88. So what remains is the finite reductive groups in characteristics L. And this is not 0, and this is not P. Okay? Okay, so these are the triples we want to study. These are also known if G is sporadic in any characteristic. So we have done this in our previous work. Again, we have done this in this memoirs. If G is an exceptional covering group of a finite reductive group, or if it's the TIT simple group. And we have also done it if it's the Suzuki or Ree group. G2 of Q, or the Steinberg triality group. So one of these Steinberg groups. So as I said, it remains this case to be considered. So we have sort of put out of our way all the small things. Yeah. No, this is in any characteristic. Unknown means no restriction on K for these groups. So for the sporadic groups, for these finitely many groups, which are exceptional covering groups, and some of them occur in different characteristics. So you are not really you are not able to tell which characteristic is it. For example, for example, what is it, U3 or 4, and well, anyway, SP something. Yeah, so there are different characteristics, but yeah, SL24 and PSL25. Yeah, A5 has two characteristics. Yeah. Okay. Yes, I think I'm quite good in time. So the main reduction theorem. This is what we proved in our memoirs. Let G be a finite reductive group, any reductive group, not assuming quasi-simplicity, but putting out of the way these sort of exceptional groups, not an exceptional Schur multiplier, not being isomorphic to a different characteristic group. Any algebraically closed field with characteristic different from P, the equal characteristic case has been settled by Gary Seitz. Okay, so if we want to check which subgroups H have the property that some of their irreducible representations induces to an irreducible representation, we may as well look at maximal subgroups, because if some subgroup has a representation which induces to an irreducible one, then there is some maximal subgroup on the way, which has the same property. Okay, so suppose that this is the case, and that we may assume that H is maximal. Then it's a parabolic subgroup. Isn't this beautiful? Well, of course, it is expected that it's the parabolic subgroups, because these are the large groups. If the group is too small, then the index will be way too large, larger than the degree of any irreducible representation, and then it cannot be an irreducible representation. But it was a hard time to get out of the way all the cases where there are subgroups which are quite about large enough, you see. Anyway, but this is the general result. And this is not true for some of these, because of course in this case you are not able to tell which are the parabolic subgroups. Okay, again, this situation, characteristic not equal to P, so this result is in any characteristic except the defining, the characteristic 0 included. This again is the same. So let's look at parabolic subgroup. So P is a parabolic subgroup. It has a unipotent radical. It's the set of matrices where you have identity matrices here. So this is the unipotent radical. It's a large subgroup. It's OP of the group, OP of the parabolic subgroup, the largest P normal subgroup. So assume that you have an irreducible module of P which induces to an irreducible module, and then U is in the kernel. U must be in the kernel of this. So in other words, it is what is called parabolically induced or Harish-Chandra induced. So this was really the thing that got us started. So this was one of the first lemmas we had, actually, back in 1999. We already knew this. But then to show that only parabolic subgroups can be used was the second. So anyway, so now we are in the world of Harish-Chandra induction, and here I feel very at home. So this allows to use all the methods of Harish-Chandra induction. So you can use while groups, you can reduce aspects to induction in while groups or aspects to induction in Ibahori-Hecke algebras. So this is why these Ibahori-Hecke algebras are so important. And this result, the previous result and this result, they are valid in any characteristic except for the defining. Okay, now in the last 5 minutes, let me talk really about a formulation of one part of our work. So first of all, you have to understand LUSZTIG series. So now I'm restricting myself again to characteristic 0. So if you have a group, it comes with a dual group. So the dual pairs are SLNQ, PGLNQ. So if this is G, then this would be G star, and SPNQ are SON plus 1Q are dual pairs, okay? So every group comes with a dual group. You have a partition of all the irreducible characters, so these are the irreducible characters over, well, any algebraically closed field of characteristic 0. They are partitioned into a disjoint union of Lustig series, and the parameters here run through the conjugacy classes of semi-simple elements in the dual group. Now, if you have a group like PGL and Q, it's easy to to parameterize the conjugacy classes of semi-simple elements. That's just linear algebra, essentially, just linear algebra. And if it's too difficult for you, because it's a quotient group, you first classify all the semi-simple elements for GL and Q, and then you see how this, descends to quotient group. So here's one of our results. If the centralizer, well, this is, I think, this is more or less due to Lustig. So this is the Lustig part of the result, I would say. If the centralizer in the algebraic group, so to formulate this result, we need the algebraic group. We need the algebraic group. If the centralizer is contained in a Levy subgroup of the dual group, so S is an element in the dual group. If the centralizer is contained in the Levy subgroup, which is split, so it's contained in an F-stable parabolic subgroup, and itself it's F-stable, then every character is Harish-Chandra induced from L in this Lustig series. So this is just, it's just a matter about looking at these semi-simple elements and their centralizers, classifying those which lie in Levy subgroups, which can be done, which we have done. And we have a converse. Suppose this is not contained in a proper split Levy subgroup. So here, of course, you could allow L star equal to G star, then you wouldn't gain much. But anyway, the formulation does not need that L star is proper. But for the converse, I want L star to be proper. Then every element is not Harish-Chandra induced from any other thing, whatever. No, I don't talk about proper here. No. Then it's not Harish-Chandra. So this is what I called Harish-Chandra primitive. It's not Harish-Chandra induced from a proper Levy subgroup. But the condition is that the centralizer should be connected. So this is not always the case, as you can see in PGL2Q already. So this is about what we got last year. Okay? So, and you see, if the algebraic group has a connected center, then the centralizer will always, of the dual group. So if G has a connected center, the algebraic group G has a connected center, then in the dual group, the centralizers of semi-simple elements will be connected by result of Steinberg. So this is why we had to restrict ourselves to groups G arising from algebraic groups with connected center. But now, well, in particular, these elements where the semi-simple element is just the one element, these are sort of very important, this is a very important subset of all the characters, the unipotent characters. They are all imprimitive because the centralizer is, of course, it's the whole group. Cannot be contained in a proper Levy subgroup. Now, if the center is not connected, what do? We get a similar formulation. You see here we need the center. This is what we want somehow. Centralizer should be contained in something, but it's not just enough to look at the connected centralizer. We have a generalization of Lustig's Jordan decomposition. Well, this is rather technical, so I'm not really going to tell you much about this. On this set, EGS, so this is one of the Lustig series corresponding to a semi-simple element. Lustig defines an equivalence relation. And then on the centralizer of the element S in the dual group and its connected component and the unipotent characters of them, the whole centralizer acts, because this is a normal subgroup in here, it permutes the unipotent characters. So you will have the orbits, and then there is a bijection between these equivalence classes and these orbits here, which I would write like this. So the offshot is, in a sense, we can parameterize the characters in one of these orbits by an orbit of unipotent characters in the centralizer. Okay, let's assume that we know this. So now the description of whether this chi is Harish-Chandra induced from something depends on this lambda as well. In the previous situation, it only depends on S, only on S. Now it depends on this lambda as well. This is why I have to bother you with this lambda. Now you need that the centralizer, connected centralizer is connected in here, and the finite centralizer is contained in here, but only that part which fixes lambda. So this group acts on the unipotent characters. Lambda is one of them. Take the stabilizer. This must be contained in L as well as the connected centralizer. If this is the case, then chi is Harish-Chandra induced from L. And we have a converse for simple and simply connected groups. So again, this part is not so difficult. Only takes about 18 pages. And the other part takes 50 pages, because we have to classify things, you see. If G is simple and simply connected, so we have a list of all these groups, and then if chi is Harish-Chandra imprimitive, which means it's induced from somewhere, Harish-Chandra induced from somewhere, then it is Harish-Chandra induced because the situation here arises, because of this situation. And there is some Levi subgroup such that this condition is satisfied. Now, of course, these 50 pages we have, they classify exactly those pairs S and lambda where this condition is satisfied and where it is not satisfied. Oh. Anyway, so let's look at one example, the case of SLNQ. And again, we describe everything in terms of GLNQ. We take, then the group is self-dual. We write a semi-simple element S in its semi-simplicity decomposition. So the SI are the homogeneous components. So SI is made up of a direct sum of equal matrices. All of them have an irreducible characteristic polynomial. These are the eigenvalues. Then the centralizer is this direct product of general linear groups over extension fields, where di is the degree of this minimal polynomial of Si. The characters are parameterized by pairs, so this is the same S and lambda is a unipotent character, but the unipotent characters of a general linear group are parameterized by partitions. So we have an E-tuple of partitions of Ni. So this is the label, this is our label, S and lambda. It's an S and the E-tuple of partitions. And then take any constituent of the restriction of chi to SLN. And all of these constituents behave the same way. They are all either Harish-Chandra primitive or Harish-Chandra imprimitive, because they are a conjugate under the group G. And then this is Harish-Chandra primitive, which means it's not induced, if and only if all the Ni's are equal, all the Di's are equal, and all the pi i's are equal, and all the eigenvalues. So these are multisets of eigenvalues. I count them with multiplicities. Well, they cannot be equal, but they are related just by the set of eigenvalues. They are just related by the scalar multiplication of some scalar in FQ. If and only if. So it's easy to write down all these elements. And this is where I want to stop. Thank you very much. Yes? Sorry. Yeah. All these exceptions are sort of contained inside the groups we have considered Previously, those groups which have an exceptional Schur multiplier, like this twisted E6 of 2, and those groups which have two different characteristics. I think there are 16 groups or something, or 14 groups. But apart from those, there are no exceptions, even if the group is not quasi-simple. So it also works for SL2 too. So it's a result about parabolic induction. So if you induce from a parabolic subgroup and you get something, so this is a result about parabolic induction. If you reduce something from a parabolic subgroup and you get something irreducible, then it must be Harish-Chandra induced. In all cases, yeah, I think in all cases. Once you know, I think, yeah, the proof does not make any exceptions. It's just you consider the opposite parabolic, and then you fiddle around with just Frobenius reciprocity. I can show you if you like. It is quite general. It's not so difficult. Sorry, I have some examples. Yeah. 11, yeah. Let me see whether I can find it. Yeah, I know. Not so far away anymore. Next, yeah. No, of course not, because we don't know all of them or their irreducible representations. We know the irreducible representations of the sporadic groups for 19, I guess, of them. For 19. And not in all cases we have checked whether the representation fixes a form, or if it fixes a form, which form it is. You see, it is very difficult if you have a representation of even degree, and you show that it fixes a quadratic form, and it's over a field with characteristic 2, and there is no way to decide whether it embeds into omega minus or into omega plus, except for fiddling around with the representation and the computer. We have no theoretical means. This is very unfortunate. So this is something for the young people here. Yeah. You have an even dimension. If you have a representation of a finite group, which is absolutely irreducible, and embeds the group into an even dimensional orthogonal group of characteristic 2. Decide whether it has width index, whether it has maximal width index or not.